Yeah. Okay, I think it's on now on YouTube. Yeah. Okay, Professor Ian, can we start?
Sure, if it's
Yeah.
good. Yep.
Professor Wahyu.
Okay.
Aberdeen. Okay, just moment, Professor Ian. Okay, I just want to. Okay.
Exactly what I imagined the mathematician to look like.
Okay. Good afternoon, everyone. Participants from Southeast Asia, from Indonesia, Philippines, Malaysia, and Thailand. And I would like to welcome Professor Ian Wanless from Monash University, Australia. And good afternoon there. Now, I think it's maybe around 5 o'clock in the afternoon in Australia. Is that right?
That's correct. Yep.
Okay. So welcome again to Combinatorics today's series. This is the 3rd episode of this year. And I'm very, very happy to see you again. First of all, I would like to extend my gratitude to our Dean, the Dean of Faculty of Mathematics and Natural Sciences, ITB, Professor Wahyu Sri Kutomo. And welcome to all colleagues, friends, and students from Indonesia, from ITB, of course, and then UGM. Hello? Okay. From UGM, from UI, University Jember, University Merdeka, Ubaya, UPI, Gunadarma, and many others. And also from Philippines, I saw some from UP, Ateneo University, Mindanao State, Cebu, Caraga State, and others. And of course, from Malaysia, University of Malaya, UBN, and USM, and also from others countries. This Combinatoric Today series is organized by the Combinatorial Mathematics Research Group, Faculty of Mathematics and Natural Sciences, ITB. And in this series, we will bring you prominent combinatorists throughout the world to give us a progress and development of the current development of the combinatorics and graph theory. And in this year, 2021, we are very, very glad to be able to present you 10 prominent speakers from various countries to share their expertise with us in the Combinatoric Today series. Some of them from Australia, from France, Germany, India, Japan, Spain, and United Kingdom. And this afternoon, we are very excited and honored to have Professor Ian Wanless from Monash University, Australia. And his talk will be on diagonally cyclic Latin squares and will be moderated by Dr. Rinovia Simanjuntak. Before I hand it over to Dr. Rinovia, I would like to invite the Dean of Mathematics and Natural Sciences, ITB, Professor Wahyu Sri Kutomo, to give a welcoming speech. Professor Wahyu, time is yours.
Thank you very much, Prof. Eddie. First of all, I would like to express our sincere gratitude to Professor Ian Wanless for your willingness to be here to present your presentation on the diagonally cyclic Latin squares in this valuable Combinatoric Today series. Actually, according to Prof. Eddie, this is the 3rd event of this Combinatoric series. So I would like also to welcome all the participants from all over the places, from Indonesia as well as from abroad. I hear there are some participants from other countries, from Prof. Eddie, and I hope that you will obtain or you will get new knowledge or deep insight on this combinatoric related topic presented by Prof. Ian Wanless. As we know that combinatoric is the mathematics of counting and arranging, and it is very useful in many aspects, and one of them in computer science. It can be used to develop the estimate about how many operations on a computer algorithm, and also it is very important in the study of discrete probability. And I hope that Professor Ian's talk will also give broaden comprehension to our young researchers and young students here in Indonesia, Ian. And for that, we thank you very much. And I hope that this won't be the last collaboration between our faculty and your institution there. So again, thank you very much from us to Professor Ian Wanless, and also to the organizing committee led by Prof. Eddie and also Rinovia and other friends. Thank you very much, and please have a joyful seminar with Professor Ian. Thank you very much.
Thank you very much, Professor Wahyu, our Dean. And now I would like to ask Dr. Rinovia to share this talk. Please, Rino, your time is yours. Time is yours.
Okay, thank you, Pak Edi. So in today's Combinatorics today, our speaker will be Professor Ian Wanless from Monash University. And before I will ask Ian to start presenting his talk, I will give just a little bit of introduction about Ian. So can you see the slide now?
Yeah.
Okay.
Yes.
Okay. So Ian graduated from Australian National University for both his bachelor and also PhD, both in mathematics. And he obtained his PhD in 1998 under the supervision of Professor Brendan McKay. And Ian is now a professor in Monash University, actually since January 2014. But before that, he also had positions in Monash University, various positions, and also in Charles Darwin University, in Oxford University, and also in Melbourne University. Ian has already published 3 book chapters and about 115 journal articles in various topics in combinatorics, which include, of course, Latin squares and also some problems in graphs and hypergraphs. And there are many awards and achievements from Ian. He has 2 medals from the Institute of Combinatorics and its applications. The first one is Kirkman Medal in 2002, and the second one is Hall Medal in 2008. He also was awarded the medal from the Australian Mathematical Society in 2009, and the latest one was in 2017, which is the B.H. Newman Award from the Australian Mathematics Trust. So I think that's all what I can say about Ian. So probably without further ado, I will give the stage to Ian, and you have 60 minutes to present your talk.
Okay. Let me.
Okay, I will stop share first. Wait.
I think maybe this will work. Okay, so thank you very much to Eddie for the very kind invitation, and to Reno for that introduction, and also to Professor Sri Gutomo for welcoming me. It's one of the few good things I think about the pandemic is that we can do more of this sort of thing and bring communities together from many different places. I would much prefer to come to Indonesia and see your beautiful mountains and so on, but it's not possible at the moment. So this is the best that we can do. But I think it's a great initiative that you've undertaken to bring people together in this way, and I'm very pleased and honored to be a part of it. So the topic that I've chosen to speak about today is diagonally cyclic Latin squares. And actually, I wrote a survey on this topic. It's quite a long time ago now. I think it was published in 2004. If anyone's looking for more background after this, that would be a sensible place to start. I'm not going to talk too much about what was in that article because I want to concentrate on more recent things. I will mention a few things that happened before that article was published, but I want to work up to discussing things which I've been doing much more recently, which relate to this topic. And I guess that's appropriate given that's the Combinatorics Today seminar. So it is about current research. But yes, these are objects which I've obviously had a long fascination with, and which I'm always amazed at how useful they are for many different problems. And I will try and give you a taste of that today. But let's start. Oh, and before I go on, I should mention that the new results in this talk will be either joint with a student of mine, Jack Alsop, who's currently doing honours with me, but is doing impressive research already. And so some things will be joint work with him, and others will be joint with Alice Trapal, who is from Charles University in Prague. But let's start with a definition of the objects that I'm seeking to talk about today. So a Latin square, I like to think of a Latin square as just a two-dimensional permutation. So it's a matrix. Each row and column is a permutation of the same set of symbols. So examples of this you will see as a completed sudoku puzzle, if you like doing that sort of thing. Also, if you write down the operation table of any finite group, you will get a Latin square. So they're mathematically important, but also entertaining. And so that's the defining property. Each row and column is a permutation of the same set of symbols. In this particular talk, I'm concentrating on Latin squares that have the additional property that the symbols occur in a particular order down the diagonals parallel to the main diagonal. So the main diagonal, in this case, goes 0, 1, 2, 3, 4, 5, 6. I've chosen to use symbols 0 up to n-1, I guess, where n is the order of the square. And I see them in order on the main diagonal, but not just on that diagonal, also on diagonals that are parallel to that. So I've highlighted one of them here in red, 5, 6, 0, 1, 2, 3, 4. That's what I mean by a broken diagonal parallel to the main diagonal. And you can see here, it's an order 7 square. So there are 7 diagonals parallel to the main diagonal, including the main diagonal. And in each of them, you see the symbols occurring in that same cyclic order. So this is the object that I'm studying today, the diagonally cyclic Latin square, and I will sometimes abbreviate that to DCLS on the slides. So the first thing you notice about a DCLS, or a diagonally cyclic Latin square, is that it is determined by any one row. If I give you for example, the first row, then you can work out what the second row is, because along each diagonal, you can just increase each symbol by 1, and that will give you the second row. And then from that, you can get the third row, and so on. So in fact, starting with any row, you can determine the whole square. And likewise, if you prefer, you can start with any column and determine the whole square from that. So that means that you can actually specify these things very compactly, should you need to store them or report them in a paper or whatever, which is one advantage. But let's have a think about what first rows would work. So, if I write any arrangement of the symbols in the first row, will it give me a diagonally cyclic Latin square? Well, let's suppose that I index my columns by 0 up to n-1, and in those positions I see some symbols which I'll say theta of the index, so theta of 0, theta of 1, theta of 2, and so on. Obviously, if I'm going to do that, I better write down a permutation for that row, because by definition, every row of the Latin square is a permutation. So that's one condition. I have to make sure that what I write down is a permutation. But is that enough? Well, by the same argument that tells you that that the first row determines every other row, it's not too hard to see that if you write down a permutation for the first row, then it will also produce a permutation in each subsequent row. So if all the symbols that I write down in the first row are distinct, and then I increase them each by 1 going down the diagonals, then they will all be distinct in the second row, and so on. So if I write down any permutation and develop it along the diagonals, then I will certainly get permutations in each row, but that doesn't guarantee that I will have permutations in each column. So let's have a think about what might go wrong in the columns. So what might go wrong is that I see things repeated in a column. Suppose at the head of the column, I'm looking at column B, and I'm at the head of that column, I have theta of B, and maybe it is equal to something else further down. That something else will have been developed along the diagonal from an entry in the first row that I wrote down. Let's say it came from column A, and it was theta A. And that theta A, as I step down this diagonal, I have to go B minus A steps, because that's the difference between these two columns. So the symbol that I see here under this one will be theta of A plus the difference between these two columns. And the problem will arise if this entry is equal to this one. So, and it doesn't take you too long to realize that that's the only problem. This is the only thing which will prevent me getting a Latin square if I write down a permutation and try and develop it into a diagonally cyclic Latin square. The only problem will happen if I get these two things being equal for some A and B. So all I need to do is to legislate that that doesn't happen. I can say I want a permutation such that these two things are not equal. And actually, it's a bit neater to put the B on the other side, because then I have a difference between f of A, not f of A, theta of A minus A and theta of B minus B. I want those two things to be not equal. And that's actually all that I need in order to get a Latin square. So this leads very naturally to the idea of what is called an orthomorphism. Sounds a bit like automorphism, but it's not the same thing. So orthomorphism is and this can happen in any abelian group, but I have been talking about it using the cyclic group as my index set for the rows and columns. So an orthomorphism of a group is a permutation of the elements of the group such that this map that sends x to the function of x minus x is also a permutation, because on the previous slide I wanted all of these things to be distinct. So this is exactly the notion that I need in order to get a Latin square. And let's make it concrete with an example. So my example will be in the cyclic group of order 13. So here are all my values of x. Here's my values of theta of x. So this is the permutation that I will write down in the first row. And if I then calculate this row minus this one, so I have 0 minus 0 is 0, 2 minus 1 is 1, and so on. 8 minus 4 is 4. 4 minus 6 is minus 2, so that's 11 in this case because I'm in Z13. And you'll notice that this row is also a permutation of the elements of Z13. So I started with a permutation, and I subtracted the identity, if you like, the identity permutation, and I got another permutation. And this is exactly what I require for it to be an orthomorphism. And by what I've explained so far, in order to get a diagonally cyclic Latin square from the permutation that I write down in the first row, the necessary and sufficient condition is that that permutation should be an orthomorphism. So orthomorphisms and diagonally cyclic Latin squares are basically the same thing. Okay, hopefully that is clear. Now, up till now, I've been working in a cyclic group, but it turns out it's often convenient to also work over other algebraic structures. So there's a natural way to generalize this to finite fields, which I will now explain. But the best way to think about this is to not think about the matrix so much of the Latin square, but to convert the matrix into a set of triples. So the matrix is specified by saying in each cell what symbol you put there, and that's giving me a triple, which is the row, the column, and the symbol that I put in that row and column. Another way to phrase the definition of a diagonally cyclic Latin square is that this set of triples has an automorphism. Anytime I have a triple with a particular row, column, and symbol, if you think about what happens to that triple as I move down the diagonal, I increase the row by 1, I increase the column by 1, and the diagonally cyclic property says that the symbol should increase by 1. All these plus ones are, of course, happening within the cyclic group in the case that I've talked about so far. So if you have a set of triples that has this as a symmetry, that whenever you see a triple RCS, you also get R plus 1, C plus 1, S plus 1, then that's the property you need in order for it to be diagonally cyclic Latin square. And of course, if you repeat this step, it will allow you to get from RCS to any R plus A, C plus A, S plus A, just by adding 1 A times. So this is a symmetry of the Latin square, and from there, it is actually very easy to generalize to finite fields. So rather than using a cyclic group to index the rows and the columns and to specify the symbols, you can use the elements of a finite field, and then you can specify that you want this automorphism for any fixed element of the field. You want it to be the case that whenever you have a triple in a particular row, column, and symbol, then you will also have all of the things you get by shifting that by any constant field element. And this doesn't lead to something that's visually quite so striking as the example that I started with, because the finite field doesn't have a natural order to put the elements in, and so you can't necessarily see the structure as obviously as you can with the cyclic group, where there's an obvious order and you get these diagonal stripes on the Latin square. But actually, all of the algebra and all of the things I'm talking about today still works perfectly well for this case as well. And of course, finite fields are very useful things and crop up all the times in combinatorics, and that's no exception in what I'm studying here today. I will just make another note about what's going on here. One of the reasons that these diagonally cyclic Latin squares are so amazingly useful is that they have a lot of symmetry. The fact that I'm imposing this orthomorphism here means that the structure that I'm producing has a lot of symmetry. It has n symmetries, if n is the order of the Latin square, or the order of the field, or whatever I'm using as the index set. And that's quite a lot of symmetry, which allows nice properties to be obtained. And that's one of the reasons why these things are really useful. Okay, and there's actually another thing which is equivalent to orthomorphisms and diagonally cyclic Latin squares, and that is to do with transversals. So I need to explain what a transversal in a Latin square is. Here I have a Latin square. It's on 4 symbols, and I have chosen some of them highlighted in green. And the ones that I've chosen have one representative in each row, one in each column, and one of each of the symbols. Over here, again, I have another Latin square on 4 different symbols, but I have chosen one of them in each row, one in each column, and one of each symbol. And those structures are things called transversals. They are actually among the oldest objects studied in combinatorics because they were studied by Euler back in the 18th century. And they have a long and fascinating history, which I won't be talking too much about today. But one of the things that Euler observed is that if you write down the addition table, the Cayley table for the cyclic group, then that Latin square will have a transversal if and only if the group that you're working in has odd order. And that's particularly relevant for us today because it turns out that whether the group has a transversal is exactly the same question as whether it has an orthomorphism. So let's see why that is the case. If you think about the Cayley table of the group and you choose these triples here. So for every row, you look in the column, you look in, no, it's not going to, you look, it doesn't want to highlight. Okay, so in each row X, you choose the symbol in theta of X minus X, where X is your orthomorphism. In that column, the symbol that you see will be theta of X because by definition, the element is the sum of the row and column index. So if I look in this row and this column, I will see this symbol. I do that for each X, and I will have chosen one thing from each row, but I will also have chosen one thing from each column because this map is a permutation, and I will have chosen one of every symbol because this map is a permutation. And so if I have an orthomorphism for a group, then that group table will have a transversal because I can just choose these elements. And it turns out it's an if and only if. It's not hard to go backwards either. If you, so that was starting with a orthomorphism and building a transversal. If you give me a transversal, then it's not hard for me to form an orthomorphism from it using a similar sort of idea. So having a transversal in the group table is the same condition essentially as having an orthomorphism. And this has an important corollary because of Euler's result, which is that diagonally cyclic Latin squares using the cyclic group as your index set don't exist if the order is even, but they do exist if the order is odd. And that's a bit of a shame because as I'm going to try and convince you by the end of the hour, these are extremely useful objects, and it's just a shame that they don't exist for even orders, but they do exist for every odd order by this theorem. So that is a limitation on what we can do, but it is the case that you can do similar things, not quite as pretty, with even order cyclic groups, where you have an orthomorphism of order n-1 rather than an orthomorphism of order n. And those things are called bordered diagonally cyclic Latin squares. You can also use, for example, there are some finite fields of even order which you can use orthomorphisms in to build these more generalized diagonally cyclic Latin squares of those orders. So all is not lost. Anyway, let's think about ways that we might build orthomorphisms. So, because it's obviously key to this question of how can I build diagonally cyclic Latin squares? I want to build orthomorphisms. And an obvious place to start is with a map which just multiplies every element by a fixed quantity. So choose some lambda in your cyclic group or your finite field, multiply every element by that, and ask, will that give me an orthomorphism? And actually, often it does. The condition you need is, obviously, this has to be a permutation. This map itself has to be a permutation, but also this map minus the identity map has to be a permutation. So I need this and this to both be permutations. And in the cyclic group, that boils down to saying that you need this, this constant lambda to be relatively prime to the order of the group. And you also need lambda minus 1 to be relatively prime to the order of the group. So if both of those things are true, then this map will be an orthomorphism in the cyclic group. And things are even simpler in finite fields, because the only problems, the only lambdas you can't choose then are 0 and 1. If you choose 0, then obviously this map is not a permutation. And if you choose 1, then this map is not a permutation, because it's just mapping everything to 0. But if you choose any other field element, then in fact, multiplying by that field element gives you an orthomorphism. So that means in finite fields, we have n-2 linear orthomorphism. By linear, I mean just multiplying by a constant. So that's the simplest sort of orthomorphism. The next neatest way to build orthomorphisms, at least in the case of finite fields, is to use the structure of the multiplicative group of the field. So you can start with a, so first of all, we know the multiplicative group of a finite field is cyclic, and it will have subgroups of any order that divides the order of this group. This group is, of course, everything except 0 in the field. So if the field has order q, then this has order q minus 1. For any divisor of q minus 1, you'll have a subgroup of that size, and you can look at these things called cycloatomic classes, which are those subgroups and their cosets. Okay, and what we do is we sort of make things linear on each of these cycloatomic classes. So in the linear orthomorphisms on the previous slide, I just chose one multiplier and multiplied everything by it. For these ones, I look at each coset of my chosen subgroup, and I multiply everything in that coset by the same element, but maybe use different elements for other cosets. And this is a generalization of the idea of the linear orthomorphism. And I'll always map 0 to 0 just because it's not in this set, and it's simpler to just keep it mapping to itself. So actually, the example that I gave you earlier is one of these cycloatomic orthomorphisms. So this was the example. These were my elements of Z13. which I'm now thinking of as a field of 13 elements. This was my orthomorphism, and if I look at now theta of x divided by x rather than theta of x minus x, obviously 0 is a special case and it's just doing its own thing. We're not including it in f star, but in all the other cases, I can divide theta of x by x, and you see that I get only 2 different values here. So sometimes I get 2. So 1 is being doubled, 3 is being doubled, 4 is being doubled, and sometimes I get 5. So 2 is being multiplied by 5 to get 10. 5 is being multiplied by 5 to get 25, which is otherwise known as 12, and so on. But there's only 2 different values here. And if you stare at this example a little bit longer, then you'll realize that what's going on is that I have split up f star, so the non-zero values in Z13, into the quadratic residues and the quadratic non-residues. So the things that are squares, so things like 1, 4, and 9, but also 3 because that's 4 squared in Z13 and so on. So all of the squares are being doubled and all of the non-squares are being multiplied by 5. And I think that's a particularly neat way to build a permutation. It's not hard to work out the conditions that you require for this to actually give you an orthomorphism, and so this is a really neat way to build orthomorphisms, because you just need to choose one multiplier for each coset. I guess I should stress here. So this is a index 2 subgroup. So I'm looking at all of the quadratic residues form a subgroup of index 2 in the multiplicative group, and it has only one other coset, which are the quadratic non-residues. So here there are 2 cosets and hence 2 different multipliers. It's sort of linear in 2 pieces. You can think of this as being piecewise linear, maybe. Anyway, we have now the notion for linear orthomorphisms, which is what I showed you on the previous slide. This is an example of a quadratic orthomorphism where we take the quadratic residues and the quadratic non-residues and make it linear on those 2 cosets. But you can also do it for cubic and quartic and so on. And these are some of my favorite orthomorphisms, because you can specify the entire map just by saying what your 2 multipliers will be. So the 2 and the 5 here determine the entire map. And that means you actually can determine an entire diagonally cyclic Latin square just with 2 numbers. That's particularly neat. It allows you to generate these things up to very large sizes and to do investigations with them in a computationally feasible way. You can explore orthomorphisms of very large fields. So these things are not just my favorite orthomorphisms, they are also well known for being very useful for building mutually orthogonal Latin squares. So let me explain what those are. Probably some of you will have seen mutually orthogonal Latin squares, but I'll demonstrate this with the court cards in a standard pack of cards. I did a minimum of research, and I believe that in Indonesia you do know the cards that I'm referring to here. So we take all the aces, kings, queens, and jacks from standard international pack of cards and arrange them in a 4x4 grid so that each row and column has one of each suit, so a club, a diamond, a heart, and a spade, and also one of each rank, being a jack, a queen, a king, and an ace. And that's one solution to it, which of course is superposition of 2 Latin squares, which were the 2 Latin squares that I showed you a couple of slides ago. These have the property that when you put them on top of each other, you get every combination of one of these symbols occurring with one of these symbols. for example, there has to be exactly one time that club coincides with king, and it's because there is exactly one king of clubs in the pack. And if you have that property in general for two Latin squares, so you get every combination of a symbol from the first occurring with a symbol from the second when you put them on top of each other, then they are orthogonal. And these things were studied since Euler's day and are very famous in combinatorics. And it turns out that orthomorphisms are very good ways of building orthogonal Latin squares. And this is one of the reasons, I guess, why they're particularly well known. So the linear orthomorphisms work a treat in this case. So if you take in a finite field two multipliers, lambda and mu, and generate two linear orthomorphisms from them, then they will always be orthogonal. If you do it in a cyclic group, then you need the difference between your two multipliers to have an inverse. So you need it to be relatively prime to the order of the cyclic group. But what this means is in a finite field, you can get as many orthogonal Latin squares from linear orthomorphisms as you have linear orthomorphisms, because they'll all be orthogonal. And you have n minus 2 linear orthomorphisms. That gives you n minus 2 mutually orthogonal Latin squares. You can always extend that with the Latin square that has constant diagonals. So if you just put symbol 0 down the main diagonal, symbol 1 down the next diagonal, and so on, then that will be orthogonal to any diagonally cyclic Latin square. And that gives you the n minus first Latin square in a complete set from these linear orthomorphisms, which is a nice way to build a complete set of orthogonal Latin squares. But they're also useful for building other sets of orthogonal squares, not just the classical ones. So this is the classical complete set of Latin squares that will give you a Desarguesian projective plane. In 1992, Evans gave a construction for this many Latin squares of mutually orthogonal Latin squares of order P, where P is prime, depended a little bit on whether that prime is 1 or 3 mod 4, but it's basically half the size of a complete set. And he does this by taking a quadratic orthomorphism and all of the linear orthomorphisms orthogonal to it. There's little asterisks on this statement because I'm telling you a little bit of a lie. Things are slightly more complicated in one of these cases that you have to use a second quadratic orthomorphism, but I'll let you look up the details. But basically the idea is one quadratic orthomorphism and all of the linear ones orthogonal to it. It gives you a nice, large, but not complete set of mutually orthogonal Latin squares. And orthomorphisms are useful not just in prime orders. In fact, for other orders, they're also very good at constructing orthogonal Latin squares. As I noted already, you always have at least one orthogonal Latin square for any diagonally cyclic Latin square, namely the square with constant diagonals. So they're generally very good at building orthogonal Latin squares. Okay, so I wanted, so that's sort of classical motivation. I know I want to move on towards more recent things that we have discovered. So in any finite field, you can represent any polynomial by any map from the field to itself by a polynomial of degree at most the order of the field minus 1. This is a well-known result on finite fields. If your map is a permutation, then the degree of the polynomial will be at most q minus 2. And actually, any transpositions or any permutation that just swaps two elements will have this degree as a polynomial. These things are known. If your map is an orthomorphism, the degree of the polynomial will be at most q minus 3. And one thing that I set my star young student as a project as an undergraduate actually was to show that this bound is always achieved, so that there are orthomorphisms whose corresponding polynomial has degree equal to q minus 3. And he was able to find a way to prove this. So I actually showed that except for a couple of small exceptions, so there are 4 small fields where this doesn't happen, but for all other fields, there will be orthomorphisms whose corresponding polynomial has degree exactly q minus 3. We know it's at most q minus 3, but we now know that's tight in most cases. And the way you proved this was actually to find 2 orthomorphisms that differ in exactly 3 places. So it's not hard to show that orthomorphisms can't differ in 1 or 2 places. That's an easy exercise. So the smallest difference that you can have is that they disagree on 3 inputs. And we were able to show that such things with that minimum distance do exist in all but a couple of small fields. And actually this theorem implies the first one, because if you think about the difference, so if I take my 2 permutations, my 2 orthomorphisms which disagree on 3 places, and I look at the difference between them, then that function is 0 in q minus 3 places out of the q places in the field, but it's not 0 on the other 3 places. So that tells you this is a polynomial that has lots of zeros, but is not the 0 polynomial, and that means it has to have high degree. And so the difference has to have degree what you want, and that means that at least one of these permutations has the degree that you want. We don't know which one, but we don't really care. We're able to show this theorem using this one. So that was quite good work for an undergraduate student, I thought. We actually, this has just been published in Finite Fields and its Applications, and in that paper we conjectured that in fact almost all orthomorphisms have degree exactly q minus 3. So we weren't able to show this, but I'm pretty sure it's true. It is known that almost all permutations have degree q minus 2. So this is an analog of that result, if it's true. While on the topic of orthomorphisms, I just mentioned that and their polynomials, the cycloatomic orthomorphisms have particularly nice polynomials. So this formula doesn't really give such a great insight into their structure, but the important thing here is that you have only k monomials. So in the polynomial, you know it has degree at most q minus 3. It could potentially have a lot of different terms in it, but if your orthomorphism is cycloatomic of index k, then it has only k different terms in it. So, for example, a quadratic has only 2 different terms in the polynomial. One is a linear term, and the other is this term here. So quadratic orthomorphisms correspond to particularly simple polynomials, and cubics will have 3 equally spaced powers, starting with a linear term and going like this. So that means they have a particularly nice structure. So one measure of sort of simplicity, I guess, for the polynomials is how many different monomials they consist of, how many coefficients are not 0. Actually, with a former undergraduate student, we looked at another measure of simplicity, which was all of the polynomials of small degree. So that was another study that we did, and you can look up the paper. But I want to talk about several more applications. So that's probably all I want to say about orthomorphisms. I want to talk about applications of diagonally cyclic Latin squares. And one of my favorites is to do with subsquares. So you can, in a Latin square, you can take a submatrix, by which I mean you just choose some rows and some columns and see what submatrix that induces. So if I was to take this row, and this row, and those three columns, then I get the green entries. And looking at the green entries, I see that they form a Latin square because, well, I know there won't be any repeats in the rows or columns, but the important thing here is that I have the same elements in each row and in each column. That won't typically happen if I just choose some rows and columns at random, but for those three rows and columns, I do get a subsquare. And there's another one over here in red. These two rows and these two columns induce a subsquare of order 2. And if you think about the structure of a diagonally cyclic Latin square, as soon as you have one subsquare, you'll get lots of copies of it because you have an orthomorphism that will map that subsquare to lots of other subsquares in this square. So actually, diagonally cyclic Latin squares are particularly good places to look for Latin squares that have lots of subsquares, and that can be quite useful. But you can also turn this on its head and look for squares that have no subsquares. So having a large orthomorphism is good for both properties. It's good for achieving lots of subsquares, but it's also good for achieving none. And with Barbara Manhout and Bridget Webb back in 2007, we used diagonally cyclic Latin squares to prove this theorem. For any odd order, there is a Latin square of that order that has no proper subsquare, so which you'll never see this sort of thing, regardless of which rows and columns you choose. We were building on work by lots of other people. I won't give you the full history, and the corresponding problem for even orders remains open to this day. Even orders, you can't use diagonally cyclic Latin squares, so what we were doing here won't solve this problem. It is harder for even orders, and there are some genuine obstacles. So orders 4 and 6 always do have subsquares, and the problem is mostly solved, but not completely. Anyway, that's one nice application of diagonally cyclic Latin squares. Another is looking at cycles. So what do I mean by a cycle? I should get rid of these. So if I choose these two rows, those two rows can be viewed as a permutation. The permutation maps 2 to 5, 5 to 4, 4 to 2, and that's one cycle. And I have 0 to 3, 3 to 0, 6 to 1, and 1 to 6. So these two rows give me this permutation, and I would say that's 3 separate row cycles, one of which is the highlighted green entries. So you say that a Latin square is row Hamiltonian if every pair of rows forms a single cycle. That didn't happen here. I got 3 different cycles, but you could imagine that I might get a single cycle from these 2 rows. And if I do that for every pair of rows and get a single cycle, then my square is row Hamiltonian. And you can similarly do this for column cycles and symbol cycles. I won't go into the details, but one of the places you see this is if you write down the cyclic group of prime order. It's an easy exercise to see that it will, any pair of rows will give you a single cycle, any pair of columns will give you a single cycle, and so on. So cyclic groups of prime order have this very special property. And it turns out that quadratic orthomorphisms give us other examples of prime order that are not the same as the cyclic group. And they even give us some examples of composite order, which have all of these properties. And I was very surprised when I discovered this. But with Jack Alsop recently, I've been working on another problem where we try and build things which have the row Hamiltonian property and the column Hamiltonian property, but not the symbol Hamiltonian property. So a cyclic group, in a cyclic group, these two things would imply the other. but it turns out that's not true more generally. And again, using quadratic orthomorphisms, we are able to construct for infinitely many orders, as it happens, the primes are the 3 mod 8, squares that are row Hamiltonian and column Hamiltonian, but not symbol Hamiltonian. So these have sort of structured a bit like the cyclic groups of prime order, but distinct in this way. So that's quite a nice result. That's part of his honours project. These Hamiltonian Latin squares, whether it's row, column, or symbol Hamiltonian, they correspond to a nice notion in graph theory. So in graph theory, you can have one factorization of a graph is a decomposition of the graph into one factors, also known as perfect matchings. And if your graph has the property that any 2 of those together form a Hamilton cycle, then the one factorization is described as perfect. And these things are well known in graph theory terms. They're desired and very special, and these Latin squares correspond to perfect one factorizations of a complete bipartite graph. So that's a nice connection to graph theory. They also connect to a problem I was mentioning a few slides ago, because if they have these properties, then necessarily they can't have any subsquares. It's actually even stronger. So having no subsquares is a very strong property, but being row Hamiltonian is even stronger than that again, because it's basically saying no proper subrectangles. Okay, now I just have one more application to mention, and my hour is nearly up, I think. That's the work that I've been doing with Alistair Powell, and it is a bit more algebraic in nature. So if you write down a Cayley table of a finite group, it gives you a Latin square. But if you just take a general Latin square, it won't typically be a group table. General Latin square will correspond to a binary operation known as a quasigroup. So you can take the elements of the Latin square and write them as indices for the rows and columns, and interpret that as a binary operation, telling you how to multiply one number by another. And what you get is a quasigroup. The defining property of a quasigroup is that it has to satisfy these cancellation laws. So if you have a times x is equal to a times y, then it implies x is y, and likewise on the other side. So quasigroups satisfy these properties, but they don't in general satisfy associativity. So you don't have this law being satisfied. And what I've been looking at with Alistair Powell is how badly this can fail. So we know in general that quasigroups are not associative, but can they be really not associative? What's the minimum number of triples which obey this law? And it turns out that the minimum number of triples, so I'm asking for how many x, y, and z is this law satisfied? So there are n cubed choices for triples, because I have n options for each of x, y, and z. Turns out the fewest associative triples you can have is n, and the only way to have n is if the only triples that associate are when x equals y equals z. And so such things are called maximally non-associative quasigroups, and they have some application in cryptography, which I won't mention. But we've been looking at whether these things existed. So the people who found the application in cryptography conjectured that these things never exist after extensively searching for them. And in fact, they don't exist for orders 1 up to 8. What we are able to show is that they do exist for almost all orders larger. It's a bit of a messy statement because we weren't able to resolve a few cases and then some infinite families. So we couldn't do twice a prime or 2 times the product of 2 primes which are of similar size. But we're able to do all other orders, we were able to build these maximally non-associative quasigroups. And the interesting thing, of course, for this talk is that we used quadratic orthomorphisms. So the key to the big breakthrough for this theorem, there were some other ideas as well, but the big breakthrough was realizing that quadratic orthomorphisms and the diagonally cyclic squares that they build are often maximally non-associative. And in fact, in a subsequent paper, we were able to show exactly how many of these maximally non-associative quasigroups you would expect to find. So we could estimate very precisely if you take a large finite field and you choose a quadratic orthomorphism at random in that finite field, then the probability that it gives you something that's maximally non-associative is this if your field is 1 mod 4 and this if your field has order 3 mod 4. So these numbers are small, but they're constant. So even for an extremely large field, it is feasible to just randomly generate quadratic orthomorphisms because you only need to choose 2 numbers. And it's easy to test whether you get a maximally non-associative quasigroup that way. And you can do this because there's a constant probability of success. You can just get the computer to run until it will find one. And that's useful for the cryptography application because it means you can find these things even in extremely large fields. And so we were quite happy with that result. And that's, again, quadratic orthomorphisms at work. So I think my hour is basically up. I hope to have given you a bit of a taste of several of the things that I've been working on recently, which involve diagonally cyclic Latin squares and orthomorphisms. And I'm very happy to encourage you for any problem that involves Latin squares. If you need special Latin squares with special properties, do try these ones because the number of problems that I have seen them applied to is immense. I've only given you a taste of it today, but they just seem to be really good at providing extremal behavior or interesting behavior or useful examples. And that's mostly because they have a very large automorphism group, meaning quite a neat mathematical structure, but they're not as constrained as, say, just taking group tables, which don't always do what you want them to do. So that's it for me. And I will open the floor to questions, I guess.
Okay, thank you, Ian, for a very inspiring talk. So probably we should give applause for Ian. Okay, so for questions, if you have a question, you can ask in the chat, or you can just raise your hand and ask Ian yourself your questions. So I haven't seen any question in the chat room. So probably while you're thinking about a question to ask Ian, we will take a little bit of a break and see a music video that was prepared for the commemoration of 100th anniversary of ITB last year.
Okay.
All right.
Yeah.
Wonderful.
Very good.
Thank you
Very
for
good.
the thumbs up. Yeah.
Happy birthday for happy 100 years. And I realize now I should have talked about rainbow matching, but
All right. Yeah.
Okay.
Yeah, that will be a good topic. Okay, so now we have some questions, Ian. It's in the chat. Okay, so the first one is from Atira Nawawi. What is it? From UPM, Malaysia. So I have read somewhere about the application of cosets in order to construct the group table as Latin squares. What is your opinion on this? Is that what you meant?
okay, so so certainly if you're trying to build a group table, then the group structure will be there, and the cosets of the, so if you have any subgroup of a group, then that will be that will give you a subsquare, because if you take any element of subgroup times another element of subgroup, it will give you an element of the subgroup. So that would be one subsquare in the sense that I talked about in my talk. And actually, if you take cosets of the subgroup, then a similar thing happens. You also get a subsquare whenever you multiply a left coset by a right coset. That gives you a subsquare in the Latin square. And interesting, reasonably simple exercise again is to show that every subsquare in the group table comes in this way. So anytime you get a subsquare in the group table, it comes from a coset of a subgroup. So this structure is very important in the group table. The coset structure gives you the subgroups, and the subgroups, the coset structure gives you the subsquares, and subsquares are very important. So you can choose to write the indices in an order that displays these subsquares. So put one coset, then the next coset, then the next coset, and then you will have the group table tiled with subsquares, and viewing things in this way can lead to good insight in terms of looking for transversals and so on. So certainly there's a number of times where we're thinking about the cosets is useful for the structure of the group table, and you can tell if the subgroup is normal. If the subgroup is normal, then all of the cosets have a particular structure in terms of the symbols that occur in them, and so on. So you can diagnose that sort of structure. So there've been a few papers where this structure has been important to me and to other people, doing things like looking for transversals in group tables and so on. I hope that answers your question.
Okay, so the next question is from Muhammad Afifur Rahman. So this is one of our graduate students. Thank you for the talk, Professor Wanless. For the orthomorphism polynomials, you mentioned that there exists orthomorphism with degree Q-3, whose degree is very big. Is there any results on the small degree cases?
There is. So actually, if you have a look at so a paper that I wrote with Chris Chalou in 2013, also in Finite Fields and Applications, it gives a complete list of all of the orthomorphism polynomials of degree less than or equal to 6, and some of those, so there's a few infinite families, I think, of odd degree rather, and for even degree polynomials, you only get finitely many of any fixed degree before the field gets too big. So there's actually an interesting open problem about for even degree polynomials, they can't be orthomorphisms in fields that are too big. And the question is, what is too big in this context in terms of the degree? So there is actually if you want to know the specific problem, you can look up the paper that I wrote with Chris Chalou. Yeah, so even degree polynomials tend to be harder to make them orthomorphisms than for fixed even degree. The field can't be very large. Okay.
Okay, another question is from Carmen Amara from the University of Philippines. What can be said about the autoparatopisms group of DCLS?
Right. So, okay. So I need to explain a little bit what that question means. So I mentioned that diagonally cyclic Latin squares have this cyclic automorphism. So that means that it has at least an n-fold symmetry. If n is the order of the square, then you get n symmetries from this diagonally cyclic property. And the question is asking really, can there be more symmetries than that? So the answer is yes. And in fact, sometimes there are more automorphisms than this. So you can get, well, one particularly neat case where you get more automorphisms when you use, for example, a quadratic orthomorphism. You can get extra automorphisms on top of these ones from there's a Frobenius automorphism of the finite field, and that can sometimes lead to extra automorphisms of the diagonally cyclic Latin square. But you can also get extra symmetries from so another possible type of symmetry that you get from a Latin square is by permuting these triples within the triple. So for example, taking the transpose of a Latin square is exchanging the row and the column. So it's swapping these first two coordinates, but actually there are other possible symmetries that are called conjugations or conjugates, where you permute these triples, and it is possible to get extra symmetries of that type as well. It's actually not too hard to write down the conditions under which for a diagonally cyclic Latin square to be, for example, symmetric in the usual matrix sense, meaning that if you transpose it, you'll get the same thing back again. That's an example of the sort of extra symmetry that that you can get, and it is certainly possible. So you can have up to an extra 6-fold symmetry by permuting these triples if your automorphism, if your orthomorphism is chosen appropriately. It won't typically happen, but there are special cases where it does happen.
Okay, so I think there are no more questions in the chat room. Or
I think Eddie has one.
Okay, Eddie has one. Okay, Eddie already has raised his hand. Okay, Pak Eddie, okay, please ask your question.
Thank you, Reno. So it's a wonderful and inspiring talk, Ian. I enjoy very much. You mentioned a lot of the applications, yeah, regarding diagonally cyclic Latin square and orthomorphisms. I just wonder, is there any application to Ramsey number? Recently, 2019, I just read a paper from Perondi and Carmelo. He wrote a paper about the multi-party Ramsey numbers arising from Hadamard matrices and strong irregular graph. So I just wonder, they used Hadamard matrices. Is it possible to use Latin square or special Latin square, or created from orthomorphism or so on? And this is my question.
Not for classical Ramsey theory, as far as I know, but there was something. I was playing with a Ramsey type question with someone from South Africa, and then COVID happened and it ruined our collaboration. But we were looking at a Ramsey type property for Latin squares. I'm just trying to remember how exactly it goes, but it was basically a Ramsey style argument where if you make your Latin square big enough, certain substructures would have to be present. Ramsey theory basically says, big enough graph, you'll find certain colored subgraphs or whatever. So there was you can look at some similar questions with Latin squares, sort of, what structures can you guarantee to be present if you make the thing big enough? The sort of Ramsey type questions can lead to some interesting things in Latin squares. We certainly didn't get to the bottom of what was going on. We got some partial results and then had to wind things up. There is one short paper published on that, which I can forward to you. There's an interesting question which we were wrestling with, and I can't remember the exact details, but it was of this nature of sort of, what structure can you be sure will exist if you become large enough?
Thank you very much. And the second question, I just so impressed with the work of your students, undergraduate student. You mentioned undergraduate student, yeah? So how did you guide them to get very nice results? This is a question from promoters or from supervisors, yeah?
Yeah, well, I think it's he's just a very talented student. I mean, I have PhD students who are achieving much less, so it is a pleasure when you give someone a problem and they come back with the answer, and it's I don't know, he has good insight and good work ethic and shows initiative and imagination, all the things you want from a student, and obviously, so we got one paper from an undergraduate project, and some of what I've talked about today will become a second paper in an honors project, and it is a joy when you find a student like that. And I mean, the beauty of these sorts of questions is a lot of them are not so hard to explain. Like, it doesn't take you terribly long to set up a problem. They can be fiendishly difficult to solve. I can describe, the problem of constructing Latin squares that have no subsquares. I could explain that, to a bright high school student, but it's a phenomenally difficult thing to do, to build them. But at least if you can understand the question, you've got a chance. And I guess with Jack, I was just lucky that chose right questions, that he was able to read some literature and think about and find a solution. And there's oftentimes you can't tell how hard a question is until you've solved it. But yeah, I guess the one thing I would say about that is he did try a couple of things that didn't work before he found the thing that does. So, you know, trying a bunch of different approaches is important. You know, get stuck on something, need to think of a different way to attack it, I guess.
So hard work is also very requested, right? Hard work from the students, yeah?
Absolutely.
Yeah. Okay.
Yes. So I see happy to come back for more questions, but I see some more in the chat. So there's a question.
There are some more questions, 2 more
Question
actually. So probably you can give like some short answers for these questions. The first one is from Agnes Garcia from the Philippines, I think. Is there an extension or generalization of DCLS to finite abelian groups and not only to finite fields?
There is. So you can certainly define orthomorphisms over non-cyclic groups and not over finite fields. And there are some interesting questions there. And so you can certainly define orthomorphisms, you can study their properties. There's one paper that I wrote with Doug Stones a while ago that looked at some very neat structure for orthomorphisms in other groups, not just in the groups where these things are normally looked at. And yeah, you can definitely do many of the same things in other groups. So and it can be useful to do that. Sometimes the cyclic group is not the right group to work in, and finite fields have the disadvantage that they only exist for very special orders. So there can be useful things gained by considering other groups. Actually, yeah, there's been some work I've done where it was important to look at orthomorphisms in a group that was Z3 across some other cyclic group, and some of those were not cyclic groups themselves. So yeah, it does happen, and a lot of what I said works there. So you can use this same definition for any abelian structure. You can insist on that as an automorphism, and away you go. So it's a good question. I think actually the theory there is less developed than for cyclic groups. So it's a very good question, and yep.
Okay, another one is from John Mel, also from the Philippines. Are there any special properties of Latin squares from groups related to orthomorphisms, or maybe something interesting about their subsquares?
Special properties. So the relationship between the orthomorphisms and the subsquares is not so well understood. I mean, it is the case. I did mention building things with particular subsquare properties. I would say we don't have a really good understanding of the relationship between the subsquares that you get and the properties of the orthomorphism. I mean, you can do computer experiments and you can find interesting things that way. And in the one case that I talked about, we were able to find a nice pattern which avoided having subsquares. It was part of a larger pattern which we think doesn't have subsquares, but we couldn't prove it. So that sort of indicates that we don't have a great handle on exactly what the connection is. So yeah, there's still things we don't understand there, definitely, and yeah, I guess more opportunities to do interesting research.
Okay. Oh, there is another one. Okay. From Joseph Belida, there was an article before on orthogonal orthomorphism of the dihedral groups. Any thoughts on this?
Yeah, so that's right. So you can certainly you know, I've been talking mostly about abelian groups, but then, you know, so you can define, you can certainly, you know, transversals don't care about abelian or not. You can find transversals in the Cayley table of non-abelian groups. They correspond to an orthomorphism. You have to be a little bit careful about how things work in the non-abelian case. Obviously, not everything carries across, but a lot of it does, and you can certainly build orthogonal Latin squares with these structures, and as you mentioned, people have done that looking at orthomorphisms of diagonally cyclic groups, and in some very, very deep probabilistic work recently, people have estimated the number of orthogonal orthomorphisms that you can get, or the number of orthomorphisms you can get from in particular group tables and so on. And there, I mean, I would have liked to talk about such things, but it would have taken me into much deeper territory than I wanted to go in today. But there is now result of the type that says that the cyclic groups of odd order have more transversals, hence more orthomorphisms than non-cyclic ones, and the actually have to be a bit careful what the claim is. Anyway, they have estimates of the asymptotic number of orthomorphisms in certain groups, and they can even tell you which groups will have the most. I better not say anything more than that in case I get the details wrong. But they're, yeah, abelian groups are demonstrated to have more orthomorphisms than non-abelian groups, but that doesn't mean that it's not interesting to look at the non-abelian case.
All right. So I think we already covered all the questions, yeah, in the chat room. And of course, we have limited time. There are several messages for you, Ian, saying thank you, saying hi in the chat room. So probably want to read that later on. But I think I will return the stage back to Pak Edi. Silakan, Pak.
Yeah, if you could send me a copy of the chat messages, that would be useful, because I would actually be interested in going through and reading them in more detail.
Right, okay.
But yes, thank you very much for the opportunity, and congratulations on your 100th anniversary, and on a very fine idea for a seminar series. And you know, yeah, thank you everyone for your engagement and your very interesting questions, and I would like to explore some of these ideas more, but that's the time that we have. So
yeah. Okay, thank you, Ian. Silakan,
okay.
Pak Edi.
Okay.
Thanks.
Okay, so thanks again, Ian, for wonderful and inspiring talk. So I think we all really enjoy very much for your talk. And before we end this session, I would like to present you some certificate of you for you for giving these wonderful talks. So let me present you some wonderful certificates. But I'm sorry, it's not. There are no Latin square there. But it's mentioned in the diagonally side.
Yeah, sure. Well, thank you very much.
I will send you this certificate. Yeah.
Yes.
Okay, and just let me.
Probably we should take a picture together.
Yes. Yeah. Okay. And before we take picture together, officially, I would like to invite you to come to Bandung. Yeah, next year, hopefully there are some.
Oh, I wish that we could travel. I'm not so optimistic,
hopefully.
but
hopefully, yeah, we can, yeah. So we really like to invite you to come to Bandung. Yeah.
Thank you very much, and
there's some opportunity for that. Okay. So,
and likewise, we would happily host you here if such things are possible.
Great. Yes. Okay. Now take a photo. Yep, Bu Reno.
Yeah.
Can you guide?
Okay.
Yeah.
Pak Yusuf bisa ambil ya?
Nah, saya.
So probably I will ask everyone to open the camera so we can see all your faces. Okay.
All the gallery. Yes.
So how many people now? 79. So 2 pages. Pak Yusuf bisa ambil?
Okay.
Nggak ada
Maybe
ya?
I can take the picture.
Alright. Okay. So Bu Prita,
Yeah.
thank you.
Okay, everyone get ready. Smile. 1, 2, 3.
Okay.
Okay, this is the first page. We will go to the next page. Everyone smile. 1, 2, 3. Okay.
Okay. Thank you, Prita.
Yes, thank you very much. Yes, you're
Thank
welcome.
you, everyone.
Thank you, Professor Ian.
Thank you.
Okay. So thanks again, Professor Ian.
Okay.
Okay. So see you next
Yes.
time.
Yep.
Yeah.
See you hopefully next year in Bandung.
Let's hope.
So I see Camino here. Camino,
Yeah.
thank you for coming.
Camino, thank you for coming. So Camino from
Barcelona.
Barcelona.
Yes.
In the morning there. Yeah.
Yes, very early.
Okay.
Really?
Oh, thanks a lot. Very early, yeah. What time there? Okay, and thank you again to all colleagues from Philippines.
Yeah, Joey. Thank you,
yeah.
Joey.
Thank you, Pak Edi. Rino,
Okay,
hello.
Joy, Agnes.
Hello.
Thanks a lot. It's lovely. And also to all others from Malaysia, from Indonesia, of course, yeah. All friends, yeah. Okay.
Yep.
So
Bye.
see you.
So
Bye-bye.
Ian, so we try
Yeah.
to save the chat, yeah. So I don't know how to.
Okay.
How
Thanks.
to save the chat?
Okay. All right.
Okay.
Okay.
Thank
Thank you, Ian.
See you next time.
See
Okay.
you. Bye.
See you next time. Bye-bye. Thanks
Bye,
a lot.
everyone.
Yeah.
Thank you.
Okay. Bye-bye. Terima kasih, Camino. Oke.
Pak Edi bisa nge-save ininya, Pak?
Gimana caranya?
Nggak tahu.
Saya tak. Langsung aja di copy itu aja, print screen.
Nanti yang jadi host dia akan save sendiri, Bu Rino.
Oh, nge-save-nya di mana?
Yang host nanti dia akan nge-save sendiri. Nanti biasanya ada notifikasi save chat nantinya. Siapa yang host? Yang host siapa?
Hostnya Pak Edi kan?
Saya?
Iya.
Ya, yang live YouTube ini siapa yang main live kan YouTube siapa?
Live lu saya.
Oh, nanti dia akan nge-save di komputer Pak Edi nanti untuk chatnya nanti.
Oh ya? Masa sih?
Ya. Selama ini nggak ada catatan save untuk YouTube selama ini kan selalu ada catatan untuk ini untuk untuk Zoom ini biasanya ada di komputer itu biasanya
di komputer ya atau di
komputer.
YouTube-nya atau di YouTube-nya
Enggak di YouTube, di komputernya ada semacam jejak digitalnya ada biasanya di komputer.
Ada notifikasinya gitu dari YouTube gitu ya, maksudnya ya, bukan?
Bukan.
Ini chatnya kan bukan chat YouTube ini. Ini kan chatnya dari Zoom.
Iya betul. Zoom itu biasanya di akhir itu dia selalu men-save-kan chat yang ada ke host